All right, it is my great pleasure to welcome our next speaker, Christian Greving from the Jülich Research Center. The floor is yours. Thank you.
Thank you. So at the vain hope that you would also talk about the title, which is a little bit out of proportions, I fear. With a graph and a formula in it, it would be worth its own presentation. So I will not read it. I will go directly to the meat of things which I want to present, if you allow me. And that is, I will talk about the different disciplines which we all hear about in this event. Many of them are quite different, but they have a lot of interactions. So talking about material development, device modeling, computing and memory, and lots of bio-inspired algorithms. And as I said, they all have a lot of interaction. If the one topic has found a solution, then immediately a new research topic will come into birth from another discipline. But one thing is not so often addressed, and that is how all these advantages would be living up on system level. So how to put all this together in a system level. And the answer to that is that I think that there must be a seamless interface that enhancing all the capabilities of the Memristor-based crossbar arrays and really put the advancements of these different disciplines into a system-level perspective. The Neurotech 2 project funded by the BMBF is a unique opportunity to do this because experts from materials, devices, crossbars, and algorithms are all together evolved in this project, and it's topped off with a demonstrator project which is trying to do on a system on chip an evaluation platform for all these disciplines. The evaluation then will happen on the system level with relevant performance metrics for different application scenarios. So I had to put in this banner as well. Please show up in multitude. Thank you. So let's come back to the first question, how to enable memristors on a system level. In this talk, I will try to give some of the answers. So there is a system on chip introduced in the Neurotech 2, the demonstrator chip, which is thought as a versatile research platform for bio-inspired computing. The CMOS interface on this chip, interfacing all the crossbar arrays, has different computing arrays, and the interaction has to fulfill different roles, which I will briefly talk of. And then I have some circuit examples to increase the data bandwidth and reduce the conversion energy of this CMOS interface, namely a readout for an increased ADC dynamic range, process voltage and current control at the memristor, low power consumption readout with memristor-based ADCs, and signed signal processing using a memristor sign. Many of these ideas were also followed up with patents to ensure the support for future commercialization, where the focus is clearly on system level and the analog CMOS innovations. The demonstrator chip here is thought as a versatile platform to test bio-inspired computing. The name, the demonstrator, is quite very lamely. One would think that there comes something up with an abbreviation that is near to a cute animal name, but we call it the demonstrator. So the demonstrator is a memristor co-integration based on a 28-nanometer bulk CMOS technology, and it integrates various crossbar arrays like computing and memory, content addressable memory, and spiking neural networks on one chip. There's a very flexible connectivity on this architecture. So in turn, there's a RISC-V enabling flexible interaction and control of the different arrays. There's also a chip bridge and the RISC-V AXI interface to combine several of the system on chips then on a system on PCB. The idea here really is that you can very easily then also take the same approach again for other matrices later on, so that this really is like a platform to measure then on a system level. What follows then is that the interface to these matrices clearly has to fulfill a multitude of roles. That is that on the one side, you have to contact to the central network on chip with a standard interface where you can read the data and also global commands. On the other side, you have to convert the digital signals into the appropriate signals that are used on the tile, which could be analog, could be spiked, or they could be even multi-level symbols. Then there's also the task to convert global commands like set or reset command or read into a sequence of signals which has to follow a certain time scaling in order to be done correctly. This must be done also in a way, or should be done in a way, that the digital part is reusable, whereas clearly the mixed signal part has to follow the demands of the tile. The system performance matrix at the end will be the signal integrity, which must be maintained, but then how can we increase the bandwidth, signal bandwidth, and reduce the AD conversion energy with respect to standard solutions like a standard ADC or DAX. So there are 4 examples I will talk of. One is here the precise Memristor control, enabling multi-level Memristor usage. And the aim here is that with the multi-level symbols, you can increase the data bandwidth of, as an example, computing and memory devices. Second is the Memristor sign, allowing for differential signals and for low power consumption. I will go into that a little bit more into detail when that comes up. And then the signal readout circuit converting signal currents from crossbar arrays, which is then something as an example how the readout could be done in a very low power fashion. And then the ADC readout optimization, which is nothing more than a clever way to see how this ADC is working in a fixed concept or in a fixed system and make use of the special surrounding. These tasks are presented in the typical part of the Invention Disclosure questionnaire of the Forschungszentrum, because I think that this is a good way to ask for solutions or innovations if you come to a certain problem. So, first thing is the ADC readout. It's not that the numbers would give you indicate a certain way how I will present them. So, number 4, the ADC readout optimization. What you have here is that you need for a certain number of memristors, DACs and ADCs, you need a certain dynamic range of the ADC. But in this system, you will more often change the voltage from the DACs than the memristor values. So you could assume that the memristor values are static for the purpose of reading out the signal. So what you can do is that you measure once for a given memristor settings the maximum current that could be and the lowest current that could be seen in this column, and then change the dynamic range with respect to these boundaries. And this way, talking about 8-bit DAC, 8-bit ADC, I think you could save easily 1 or 2 bit, making the area and the power consumption half, depending on what you have done to your ADC, obviously. The next thing is the precise memristor control. So the problem is that because of the parasitic capacitors and resistors you have on the control line, you have jobs and also reduced bandwidth. In addition, manufacturing mismatches result in offset voltages across the memristor. So how you can solve this is, on the upper end of the memristor, you can introduce something that is called a folded cascode. So you set a PMOS on top of the memristor with a fixed current value, and then you control the drain of this PMOS with a second PMOS, which can be then in an integration loop set to a fixed voltage value. You can see that then the signal current through the memristor is also available through this second PMOS. This is not only the possibility then to very accurately set the upper voltage of the memristor, but also it has the benefit that this node is always at the same voltage, and thereby is not reducing the bandwidth of the readout. On the other side, you can do obviously the same thing again. So either you have a regulation loop setting the lower voltage of the memristor, or what you can do for set or reset, and want to try out if this gives more accurate values then, is that you instead set the current through the memristor instead of the voltage. The third thing is a proposal for a low-power signal readout. That comes in here in this example as an ADC, where you use weight memristor values to translate an analog voltage coming in the lower left of the picture into a thermometer voltage or digital code on the outputs V1 to V4. This takes very little place, and since you can make use of the memristors to optimize this setup, you can also avoid taking a unity transistor size and sizing it up so that you can have a really small signal here. That's clearly maybe not enough to be beyond 3 or 4 bit, so you cannot take it as a readout for a complete large column, but it would be sufficient to read spikes and to avoid intersymbol interference while reading them out. And also you could maybe use them in order to have a higher bandwidth on your signal lines by sending the analog data directly and then digitize it at the target's computing array. So the last one is the memristor sign. So signals are prone to noise, limited by linear range for multi-level symbols. And also, signed signal processing would require a memristor sign. So the question I was asked was, how can we add a sign to a memristor value? And clearly that's not possible. But what you can do is that you add another memristor and another small circuitry, which are shown here on the lower side of the picture on the right side. And this circuitry changes the sign of the input voltage. So it does nothing to the memristor itself, but if you assume that you have a differential input voltage because you want to have a sign, then with this memristor value, you change the sign of the input voltage. And this follows then clearly also what is done in a multiplication or an XOR, so that you can easily, with a second memristor, which is also not so prone to the memristor value itself, can change then the direction of the output current of the memristor cell. So in itself, now you can have 4 times the signal range by really doing signed signal processing. At this stage then, I found that this is also nice to use in general, because a memristor-based crossbar is always the disadvantage that it uses power consumption as information, which is maybe not so a good idea if you really want to reduce the power consumption. So you always have a voltage across a resistor showing you a current, and this will change. This current will then change depending on the information, which is lots of power then, because you need a lot of ratio between the memristor values for reliability reasons. And so the end of the story is that you need lots of more of current than you would need in a minimum setup with the sensibility that you could reach with the minimum current. But if you only take this lower circuitry, you can, instead of changing the current value itself, you take always the same current value by adding a current source underneath the circuitry, and you just change the direction where the current goes with the help of the memristor. So it's less power consumption, and it's far more robust against memristor tolerances. A third thing, which I will briefly, because I was out of time as well, go into is that how this could be then used in spiral neural networks or oscillatory neural networks. So if you take the sine wave and maybe you would translate it into a pulse train, then you can, with a pulse train where the information is in the phase of the signal, you can easily shift the phase by inverting the signal. So again, you have the possibility with the memristor value, which does not need to be very accurate, to either shift the phase or not shift the phase of your incoming signal. And this would give a very low power, easy way to read out and value the output of, as an example, ONNs. So as a summary, I've presented the Neurotech 2 project. Thank you for that, with all the experts that are involved in this project. I've presented the system architecture of the demonstrator with a very flexible connectivity. I have presented you what requirements the CMOS interface has to fulfill, and I presented you with a performance matrix, how this will be at the end measured. So, and I have also argued why there were patents issued for these inventions, because that will, in the long run, that will support then the future commercialization. So, thank you.
Thank you, Christian, for giving us insight into your research. Are there any questions? Because Christian was on time, we have about 5 minutes. There we go.
Ted Johansson, Uppsala. Christian, very impressive work, very flexible platform. How dependent are you on the exact Memristor technology? How flexible are you on that part? Also the supplier, the technology, the material.
I think that if you change the Memristor, there could be easily changes in the Memristor values of an order of magnitude. So I think that some of the aspects could be very flexible. As I have shown the design of the Memristor, you could even add a second Memristor, and then you have the difference of these Memristor values. Then it's much easier. But I would expect that the more you are really dependent on the value of the Memristor and not where in the order of magnitude the Memristor is, the more you will have problems to take the same circuitry and use it again. I would expect that also things like spiking neural networks would be less prone to changes of the Memristor.
Have you any certain technology in mind? You had a spec or a little bit feeling for how Memristor would behave?
Yes, because the Memristors will be also co-integrated in the Forschungszentrum. So we have the details in hand, which Memristors we will taking. That is why I said that it's very fortunate that we have all the experts in this project, because we have also the people who are doing the materials and the models. Thank you.
Thank you.
Thank you. There's another question.
Hi, my name is Deepak Sharma. I have one question related to the signal integrity. So output of digital to analog converter you are giving to the Memristor through multiplexers, right? And based on the state of Memristors, you will be applying some writing pulses. So how are you taking care of the signal reflections? Because there might be the possibility of impedance mismatch when we do the high frequency pulsing. So those reflections might create disturbance to the device.
Yes.
So how it is being taken care in your case? Yeah, thanks.
I might ask you the question, what do you mean with high frequency?
So high frequencies is so Memristor writing in some devices might go from nanoseconds, let's say 50 nanosecond of the pulse that go from the digital to analog converter to the device. So 50 nanosecond I meant for high frequency, yeah.
I would assume that taking the wavelength into account, that anything that is below 500 megahertz would not see so much of these problems. And anything that is above 500 megahertz, you're completely right, you would have to face maybe reflections from impedances that are not really matched. On the other side, I think, allow me to say this, that I don't see that the Memristor crossbars are really running at 2 gigahertz now. That would be a complete different setup, which I agree is a problem which has to be solved, but that would be then probably solved with having not so much passive Memristor cells in a crossbar, but more active cells, which would incorporate then an amplifier or an impedance switch or whatever.
So around 100 megahertz also we do see some kind of peaking in the pulse, writing pulse. So in your case, how are you observing that during these writing and reading? Are you putting some extra oscilloscope, or ADC itself is, ADC must be averaging samples, I suppose, yeah.
Well, I don't get you. So what we have planned here for is that we have a regulation loop that will set the voltages, the spikes, or feed in spikes directly. Yeah. As far as I can tell, if that is below 500 megahertz, maybe you wouldn't expect so many changes or reflections. On the other side, on the output, we use this folded cascode structure, because what this will do is we'll have a very good impedance transformation. There is no voltage changing because there's only a current readout, which helps a lot then if you are talking about high frequency signals.
I see, yeah.
I hope that helped. Thank you.
Thank you. Thank you, Christian. Please just give a round of applause. Thank you.
Thank you.